Hello guys, and welcome to Lesson 12, Basic Trigonometric Identities, Double Angle Identities. First, we need to know what's a double angle identity. Okay, so talking about double angle, okay, from the idea of the term double, and of course there's an angle, this gives us the concept or the functions, specifically trigo functions, having a multiple of 2 in their input or angles. Okay, so for example, sine 2x, we have cos 2x and tangent 2x. And in fact, we are going to find the formula or the identity. Okay, we're going to find the formula or what we call the identity of this. Okay, or identities, formulas or identities. Okay, so how do we start, or where to start? Okay, so we must remind ourselves that talking about having a double angle, for example, if we have an angle, let's say let x be our angle, we can get the double angle of this by simply multiplying by 2, or if we simply add another angle. Okay, simply add another angle, and this will give us 2x. Okay, so this will be the main idea. Okay, so to start our proof, let's start with sine. Okay, so for sine, let's have the double angle of sine, which is 2x. Okay, if we try to separate this, we have sine x plus x. Okay, now observe the angle. So in our angle, we have the operation plus, and this will give us the idea of sine a plus b, which is the sum and difference identities. Okay, so we're going to apply here the sum and difference identity, specifically the sum identity of sine. Okay, and we know that this is sin cos cos sin. So we have sine A cos B, and we have plus cos A sine B, or sin B. Okay, so here, so our first angle, our A would be x, and of course our B is also x. So applying sin cos cosine, so we'll have sine of x cos of x. So b is our x here is b. Then we have plus cos a, so our a is still x. Then b sine b is also x. Okay, and if we try to rearrange, we have sine x cos x. We can actually what do we call this, switch places, because this is commutative. Remember, multiplication is commutative. Okay, so we have plus sine x cos x. So in fact, the two terms are equivalent, or they have the same elements. So if they have the same elements, if they are similar, okay, similar terms, we can actually add. So sine x cos x plus sine x cos x is simply 2 sine x cos x, and this will be the identity, our first double identity. Okay, so for sine 2x, we have 2 sine x cos x. Okay, now we're done with sine. So let's try to solve for cosine. Okay, so cosine 2x. For cosine 2x, let's say we have cos 2x. So we know that this is cosine x plus x. So for cosine, we know that cosine A, we have 2x, or plus b is cos cos. sin. So cos A, cos B, and if it's plus, it becomes minus. So minus sine A, sine B. Okay, so we know this is cos A, so A is x, cos x also, cos B is cos x, minus sine x, sine x. Okay, or we can simplify. So cos x times cos x is cos squared x, minus sine x times sine x is sine squared x. So this is our identity for cos 2x. Okay, so for cos 2x, we have some forms. Okay, so aside from cos squared x minus sine squared x, we can actually express cos squared x minus sine squared x in many different ways. Okay, so let's start and let's try to find these forms. Okay, first, we have cos 2x equals cos squared x minus sine squared x. Okay, so first, we must review our Pythagorean identity. So we know that sine squared x plus cos squared x equals 1. Okay, so this is the first one of the first identities that you have learned in part 1. Okay, so Pythagorean identity. Okay, so since this is an equation, we can manipulate this. So if we try to use properties of equality, we can also say that sine squared x equals 1 minus cos squared x. Okay, so substituting this value here, sine squared x, to our equation in cos 2x, this will give us cos squared x minus, okay, so we are going to substitute this. That's why there is a grouping symbol. It's a binomial. So 1 minus cos squared x. Okay, then if we try to simplify, this will give us cos squared x minus 1. So plus cos squared x. So we have 2 cos squared x, so 2 cos squared x minus 1. And this will be the second form of cos 2x. Okay, so aside from this, we can also have cos squared x equals 1 minus sine squared x. Okay, if we try to use the property of equality. So what if it's cos, the cos squared x that we're going to substitute. Okay, let's try. So for the third form, so we have again cos squared x minus sine squared x. So substituting this value here in our cos squared x, this will give us 1 minus sine squared x. Okay, minus sine squared x. And if we try to remove the grouping symbol, we have 1 minus sine squared x minus sine squared x, which will give us 1 minus 2 sine squared x. And this will be our third form. Okay, so this is the second form, and this is the third form, and this is the first form. Okay, first form. Okay, so we're done with the sine 2x and cos 2x. So lastly, we need tangent 2x. Okay, so how do we find tangent 2x? Okay, so for tan 2x, we have tangent of x plus x. Okay, and remember the the sum and difference identity of tangent. So if we have tan A plus B, so we have tan 1 tan. You can remember that one. Okay, so in our previous video, so we have tangent of A plus tangent of B all over 1 tan. So 1 minus tangent of A, tangent of B. Okay, so applying this formula, so we have tangent of the first angle, which is x, plus the tangent of the second angle, which is also x, all over 1 minus tangent of the first angle times tangent of the second angle, which is also x. And if we try to simplify this, so we have tan x plus tan x, we have 2 tangent of x all over 1 minus tan x times tan x, so we have tan squared x. And hence, we have the identity of tangent to x. And so, this is the complete list, okay, the summary of the formulas that we have derived from sine 2x. So, sine 2x, it's very easy to remember. So, it's 2 sine x cos x. So, sine 2x is 2 sine x cos x. So, just remember that there's a pair of sine x and cos x. As long if it's sine 2x, then the 2, okay, so the double angle is already somehow, it's kind of outside of the expression. Now, and of course, for tangent 2x, let's try to make memorize tangent 2x first. So tangent 2x is kind of similar to the sum and difference identities. So the difference is just we have instead of tan a plus tan b, we have 2 tan x. So we have tan x here, 2 tan x, the numerator, and in the denominator we have 1 minus tan squared x. Okay, so that's for tan 2x. Now, for cos 2x, so there are 3 forms. So how to remember this? Okay, so for cos 2x, always remember that the sine function is found at the last part, at the second term. Okay, and the cos function is always at the first term. Okay, so we have cos, for the first form, we have cos squared x minus sine squared x. So it's kind of similar to the Pythagorean identity, but instead of having it plus, we have minus. And of course, the first term contains the cosine, the last term contains the sine. So cos squared x minus sine squared x. Just a brief note, it should be squared. Cosine and sine should be squared. You cannot use cos 2x if the function or the expression contains only a first degree cosine and sine x. Cosine x and sine x. So you cannot apply this here. Okay, you cannot apply the double angle of identity of cosine. Now, for the second form, we have 2 cos squared x minus 1. And for the third form, we have 1 minus 2 sine squared x. So, they have a pattern. If you try to observe, there's always 2. Okay, but it still follows that the cosine should be at the first, okay, first term. So, minus 1 here. For the third, we have 1 minus the 2 sine squared x, so indicating that the sine is found at the last term. Okay, so these are the double angle identities. That's the end of explaining the concept of the double angle identities. So in the next video, we're going to have some examples about the double angle identities. See you there.